Hello, in my previous video I showed you how PowerSat can be used to show some basic functionality. I thought I'd take in this episode a little more time to go through the different fitting options that are available within PowerSat. So once again I've opened PowerSat by calling PowerSat, and I've pointed my current folder in MATLAB to just a test folder full of files. So for simplicity, I'm just going to open a file, and I'm going to open the DPPH file because it's the simplest to view. So automatically PowerSat defaults to the Gaussian fitting method. So this Gaussian fitting method basically, upon loading a file, PowerSat finds the maximum peak and the minimum peak by just averaging all of the spectra that it has available to it in that data set, and it finds the maximum and minimum point and sets them into these two boxes. From each one of those, the peak and the trough, it then sets a window around them, and this is displayed here by the peak being in the red line as we're on oxygen, and the black line being for the trough. And so the small dotted lines then represent the window around the center point, which is marked by that dashed line instead. So inside of that window it's actually looking. So for the peak, what it's done is very simply it's taken all of the spectra and then it's applied a simple logic operator. And so what it's done for the peak, it's taken everything that's above 0 and they'll consider that to be data, whereas anything below 0 there's a simple logic operator and just makes it equal 0. So for the peak, all it's concerned with is everything above 0, and for the trough it's just looking at the things below 0. So if I change the viewing option and put it onto single spectrum, we can see a little more clearly what's actually gone on here. You can see that the spectra has been fitted, and that you've got a single curve coming up and you've got a single curve coming down, where a Gaussian distribution has been fitted to both. So if I zoom out again a little bit and I just click through different powers, you can see that it generally fitted data pretty well across most of the powers. At very low power you've got a pretty good fit, and then when we go to extreme powers, so I think this goes up to at 126 milliwatts, you've still got a pretty good fit despite the actual spectrum being quite noisy. So once it's fitted, PowerSat takes this point here and it takes the point there as calculated from the Gaussian distributions, and it does the maths and converts it into this power saturation curve here, and it's given us a value of near enough 57.6. So if I change the fitting method now and I select Lorentzian, once again we have to wait a short time for it to fit, but what you'll see is near enough the same thing. Now Lorentzian pays more attention to the tailing of these curves rather than the single point maximum like Gaussian does. So what you'll see if I just click through again is that for most of these spectra you've got pretty good fitting. Obviously at the more extreme values the fitting isn't quite so good, but you'll see I think that the fitting isn't quite as good to the actual maximum and minimum peaks as it perhaps was for the Gaussian model. So if I zoom out a bit, but if I use the zoom tool here on the top, I can then actually zoom in on this window, and you can see there then that the actual fitting there is a little way off, which in turn has resulted in it giving us quite a weird power saturation curve here, and then the p half of this curve is obviously well off. So Lorentzian, whilst being more true to the data, isn't actually necessarily the best option, and with noisy data you might find that instead of giving you a curve, it will get stuck in a local minima, and it will just end up plotting you a straight line across 0 rather than actually showing a peak, which is not what we want at all. So that's great, but if you want there's the third option, which is the original option that came with PowerSat in versions 11.11, and prior to that was single point. So what single point does is it takes your peak and your trough value, and it just quite simply finds the data point that is closest to it. So again, because this is taken from the average spectrum, it's not bad for load intensity. But as we go up in powers, you might find that it starts to stray, or the line strays a little from the actual peak, which perhaps is the case here, but this example isn't actually too bad. No, I'd say that's actually very good, even at 50 milliwatts. So because this is quite a good spectrum, it's actually given us quite a nice fit, and this time we've got a p-half of 57.9, which isn't too bad at all. I'd be quite happy with that. Obviously this method isn't quite as robust when you're using very noisy data, because you may find that your peak and your trough are actually going through noise, not through the actual physical point. So the fourth method that I include is a Gaussian derivative method. Now this method is a little slower because you have to fit the first derivative, and then you have to calculate the second derivative. So what this has done now, if I zoom in a little, so what we've done now is basically an absorption graph in EPR is basically a first derivative. So if I take a first derivative Gaussian equation and fit that, we should be able to get a pretty good fit. So the first derivative, as shown by the dashed line, isn't a bad fit. I mean, it's probably not as good as actually the Gaussian that we saw before, but it's mathematically more correct. So the method now, once I've found the coefficients for this fit of this first derivative Gaussian, I can then take those coefficients and put it into a second derivative Gaussian equation, which is plotted here in the little dotted lines. And where these dotted lines cross 0 will be the turning points of the maxima and the minima, and we can then use those turning points and the coordinates for those. So I can then take the coordinate for the turning point and then calculate the actual position using the actual equation and the coefficients found for the first derivative. And then from that, it's obviously plotted this curve, which looks much the same as before, and that's given us a value of 58.9. So that's not a bad p-half either, and you'll see that that's got quite a good similarity to previous. Now obviously, I might have to zoom out a bit, but for different data sets, for different data sets, you'll see that your fitting may or may not be better. But as with all of these fitting methods, the option is entirely up to the user. Obviously with this DPPH standard there is very little noise on it, or even at stupidly high microwave powers. So the fitting is very good. For noisy data, then the fitting is basically entirely up to you. So finally, the last option that I include is the Lorentzian derivative. Once again, we're going to have to go through some fitting. And once again, what we've done is fitted the data to a first derivative Lorentzian function, which I think is actually giving us a much better fit, which is what we'd expect, as our absorbance spectrum should be closer to a Lorentzian function than a Gaussian function. And once that's been fitted, we take the parameters again and we calculate the second derivative, and where the second derivative crosses 0 is obviously the turning points for the first derivative, and then from that we can calculate the the coordinates of the maximum and minima, and then from that we can calculate our power saturation curve, and from that power saturation curve we've got a p-half of 59.2, which is again very good and very close to the other values that we've seen in the other ones. So there you have it. That's basically the different fitting methods, and obviously by using the zoom tools as well as the view single spectrum tool, you can see an awful lot of the actual raw data, and at any point if you feel like you want to export one of those, you can click on the spectra and you can detach the plot as you'd expect with as per normal, and from this you've then got your normal figure, and then you can just file and you can save it as per normal. The same thing goes if you're viewing it on single spectrum mode and you particularly fancy some method, then you can always click spectra and you can still detach the plot that way, or you can directly save the spectrum if you don't want to detach it first by clicking save plot. If perhaps you've got a very broad spectrum, you can obviously change your fitting window. You might want to make it 200 Gauss, which is going to be far too much for this, so I might make it 50 Gauss for this example. But the actual fitting window, well, this is probably easier. So now, rather than considering just this small section in the middle like it was there, it's now considering a much broader spectrum for the fitting. Now obviously that's not actually giving us much difference here because it's a very clean data set, but for if you've got a very constricted site or a very broad data set, then that might give you the extra edge for a good fit. The only last thing I'd like to point out is this error bar tick box here. By ticking that, of course it doesn't work. So basically this tick box should usually, depending on what method you're using, should give you an error bar plot, but it's not. So I'll fix that and you can look out for the fix in version 12.9. What it should be giving you is error bars to show you the 95% fitting confidence bands. Basically the 57 plus or minus the 1.3, so you have the confidence bands for each of the fitting. So there you have it. There's the additional fitting and the different fitting methods and what exactly they do. Thanks for your time and thanks for listening.